Okay, so now we have finished the part that we were talking about, namely progressive metamorphism of siliceous dolomite or dolomitic quartzite. This system is quite simple, and that is why it was chosen. Essentially, the reason being that there are very little solid solution, or most of the phases are more or less pure phases, and solid solutions are limited, although this is not entirely correct, but most phases can be understood to be more or less a pure phase, and we can deal with other aspects. The more phases become impure, then the effect of solid solution becomes very strong, and other things that needs to be talked about get sort of takes a side goes to the side, and the central theme is lost. But now we go into the system which is called progressive metamorphism of mafic rocks, and that involves invariably all phases that are solid solution phases, except if you like quartz or lawsonite, but most of the phases are impure phases. And so you can understand there will be a lot more complexity about what I'm talking about. Now, before we go into this aspect of progressive metamorphism of amphibolites or mafic rocks, there are diverse types of mafic rocks, olivine basalts, alkali-olivine basalts, quartz-olivine thoriites. You can have a huge variety of mafic rocks as well. But when I discuss this, unless otherwise specified, it takes into account a mafic rock which can be broadly called as a normal wall, an olivine thoriite. So it's very vast in expanse on the ocean floor, and we take this composition as sort of representative of the wide array of mafic rocks that you find on the Earth's surface. So essentially, the bulk composition of the rock is more or less a normal mold. Start with an olivine thoriite. Before we go into progressive metamorphism, I would like to introduce a subject which you know, but I would like to re-emphasize it, as the concept of metamorphic facies. Essentially, it's very simply stated without the frills. It is metamorphic rocks that have formed or crystallized at the same or similar PT conditions are known to belong to the same metamorphic facies. So metamorphic rocks that form or crystallize or recrystallize at similar pressure temperature conditions, same or similar pressure temperature conditions, are thought to belong to the same metamorphic facies. In other words, if you have diverse chemical compositions of rocks, and if they metamorphose at the same pressure temperature, there will be diverse mineral rocks. Say, for example, if an amphibolite, if a mica schist, or a siliceous dolomite or dolomitic quartzite, a package of it are metamorphosed at the same pressure temperature conditions, you will not get the same minerals. Why? Because although they have crystallized at the same pressure temperature conditions, they do not have the same bulk composition. And that is the problem. So you must have seen from the progressive metamorphism of dolomites that the mineral assemblage that is stable at a particular pressure temperature depends on the composition of the rock and also the fluid composition of the rock. Yes, internally buffered system, externally controlled systems, but essentially it's a function of the bulk composition of the system and the fluid composition. Similarly, that can be extrapolated to the mafic rocks as well. We take normal molds. But you can have a whole package of pellitic rocks, carbonate rocks, calc-silicate gneisses, calcium aluminium gneisses, a whole diverse kind, ultramafic rocks, and they yet may be formed at the pressure temperature condition, but the bulk chemical composition, but the mineralogy would be very different. Or, for example, you can look at it another way. if you have a particular bulk composition, say a normal mole, if you change the pressure temperature condition, the mineral assemblages would change, depending upon the temperature pressure conditions. So, a metamorphic facies are rocks formed or crystallized at same or similar pitty conditions. The mineral assemblages that will stabilize for rocks of the same metamorphic facies will not be the same. It will depend on the bulk composition. So, minerals with diverse mineralogies does not really mean that they've been metamorphosed to the same rock. Also, at the same time, a same metamorphic rock which has metamorphosed at different pressure temperature conditions will have different mineralogies. This is the same thing told in different ways. But essentially, this is what is metamorphic facies conditions. You may be surprised to know that although most of us study progressive metamorphism of dolomite, most of the universities, they have put a lot of emphasis on peletic rocks. But the metamorphism or the metamorphic facies, naming the metamorphic facies, comes from metamorphism of mafic rocks. They come from metamorphic facies of metamorphic rocks. So you don't have something like a staurolite metamorphic facies with staurolite kyanite metamorphic facies, but you have an epidote amphibolite facies. Epidote amphibolite does not form in peletic rocks. Epidote and amphibolite don't form in peletic rocks. So what happens is the metamorphic facies initially grew out of metamorphism of mafic rocks. So most of the mineral assemblages, say for example, you would say blue schist facies, which contains a characteristic mineral called lawsonite. The lawsonite forms in metamorphosed mafic rock at a particular pressure temperature condition. But lawsonite does not form in peletic rocks. Lawsonite also does not form in argillaceous or in siliceous dolomites. So we should be careful about that. The important point that I was trying to tell you here is that the metamorphic facies concept, the division of metamorphic facies, which metamorphic facies occurs, is based on metamorphism of mafic rock. There was a time, in older times, when so much equipment was not involved. People used to map isogrades, metamorphic isogrades, based on the composition of plagioclase in mafic rocks. Based on the composition of the plagioclase in mafic rocks. And this composition of the plagioclase they found out using a microscope, which can also tell you the composition of plagioclase. But you have to be good with it. There are very stringent rules to find out how to find out the composition of plagioclase. As we will see that the plagioclase composition becomes more and more anorthite rich as we go to higher and higher grades. But it's very important to know that plagioclase compositions were determined to find out metamorphic isogrades in mafic rocks. Now first let me draw the metamorphic facies diagram, which has now been reasonably well accepted. I will first draw the diagram and then I will explain to you. I will explain the details later. All of you know the names, but just for this thing, I will draw another line and then I will talk about it. Now, before we go into details of the diagram, the important thing here is this set of red lines. Here it is Andalusite, kyanite, and this is silimonite. This is merely for the reference. This is just to give you a reference to the whole perspective. None of these minerals crystallize in amphibolite fishes, in mafic rocks, in metamorphosed mafic rocks, except for some unusual compositions. Kyanite, silimonite, and andalusite do not crystallize in metamorphism of mafic rocks, having a composition very similar or identical to a normal one. So this diagram is not really linked to the metamorphic phases of metamorphic rock, but gives you a reference. The important point here, this point here, the triple point, this occurs at roughly 505 degrees centigrades, 505 degrees centigrades, and 3.7 kilobars. This triple point, we have discussed this before. This is 5 kilobars, this is 3.7 kilobars, and 505 degrees centigrades. There are error bars associated with it, but this is a good number to remember. 505 degrees centigrade and 3.7 kilobars is the triple point. And this is the kyanite field, this is the silimonite field, and this is the andalusite. Also in the diagram, there are two green lines drawn. These essentially represent wet these represent melting of granitic rocks. Melting of granitic rocks. So these are essentially solidus reactions, where you have a granite and granite partially melts. Here also granite partially melts. Now this I have written as wet melting of granite. This curve is wet melting of granite. That means XH2O is equal to 1, or the partial pressure of H2O is equal to the total pressure. And this is occurs, and the melting temperature normally moves to the high, rotates to the high temperature as the granite becomes drier and drier. That means XH2O becomes less than 1. So this gives you an idea that if you have to have melting, then this is roughly the temperature at which wet melting of granite occurs, and here melting of dry granite occurs. I have not given you the entire gamut of this thing. It's not necessary. This is again just for reference. Just for reference. That this is the curve for wet melting of granites, and this is the curve of wet dry melting of granites. In between there, granite also melts depending upon the different XH2O values. But here you can see that this curve is nearly vertical here, and this temperature roughly is about 650 degrees centigrades. 650 degrees centigrades. So melting of granites, if you have amphibolites, this here at the highest pressure and temperature of this metamorphic facies, granite melting may happen. So here on the left hand side there is no melting. And this line here, there are no pressure temperature conditions yet recorded on the earth to the left of the diagram, and so it's written not realized on earth. No metamorphic pressure temperature has been numerically determined on the left side or the lower temperature part of this diagram. So effectively this part is not our domain. Now these are some of the boundaries. This is called the zeolite facies. This, as you know, is called the zeolite facies. We will go into the details a little bit here. This is called the zeolite facies. This is called the prainite pompiliite facies. This is called the blue schist facies. And this is called the eclogite facies. Here you have the green schist facies. Then you have EA, epidote amphibolite facies. And then you have amphibolite facies. And then you have granulite facies. So these are the different metamorphic facies. And the nature of the boundaries are like this because they essentially represent a particular reaction. So there are, I will go into the details of this. So this line, for example, marks the lower boundary, it's a reaction boundary. It marks the lower limit of the eclogite facies. For a normal mob, for the condition P total is equal to pH2O. Very important. P total is equal to pH2O. So the pressure and pH total for this condition and for a normal mob, this is a reaction that sets the limit of the lower limit of the eclogite facies. Similarly, say for example, here this is the boundary between the amphibolite facies and the granulite facies. Essentially, why these boundaries are? Because these are reaction boundaries, and we will talk more about it later, so I'm not living in. All these lines that I have drawn are essentially facies boundaries. So across the boundaries, something interesting is happening. Some reactions are reacted out, some reactions are reacting in, but essentially these are facies boundaries. So once again, eclogite facies, blue schist facies, prainite pompiliite facies, zeolite facies, one sect here, and this, if I mark here, this arrow, blue arrow, this marks zeolite, brainite, prampelite, blue shish to eclogite. This is called the another reaction, but another blue line is this way, and another blue line is this way. What is happening here in this line? You have andalusite kyanite. At low pressure you have andalusite. At high pressure you have kyanite. So it is, if you compare the red diagram, so this is called also, these are called the different baric types. Baric type means here the pressure increase is more dramatic than the temperature increase. So this is called the high pressure baric type, and essentially this is also called andalusite kyanite baric type. Then you have this blue line here. This is typical for contact metamorphic rock or low pressure baric type. So this is low pressure by temperature. This one is high pressure by temperature. Here the transition is from andalusite to siliconite. Andalusite to siliconite. Here it was andalusite to kyanite. And this is the intermediate type, pressure by temperature. There you have kyanite to sillimanite transition. Have you understood? Kyanite to sillimanite transition. So in this metamorphic phases diagram, we have three different baric types. You may have red Barrovian zone sequence. That's an interpressure. That is an interpressure. Or you have heard Sanbagawa. That's the three baric types. Without going into the names, there's a high pressure by temperature baric types. So you will get zeolite phases at the low pressure, brainite, pampelite, blue schist phases, and eclogite phases at the highest pressure. Here you will get green schist phases, amphibolite phases, and granulite phases at low pressure. And here you will have green schist phases, epidote amphibolite phases, amphibolite phases, and granulite phases. This is the sillimanite kyanite baric type, andalusite sillimanite baric type, andalusite kyanite baric type. So this is all that we have from the metamorphic phases diagram. So this is what happens. So you can see here quickly that for high pressure metamorphism, you're not expected to get a lot of melting because this curve becomes asymptotic straight, and this is a high pressure, so you will not be able to generate melts at even high pressure. Not impossible, but normally it is not a very common thing, although you do get it. And this is where the high pressure temperature you will have low pressure assemblages, intermediate pressure assemblages, high pressure assemblages. These are the three baric types. Having said this, now I will tell you a little bit about the different minerals in the metamorphic phases. Maybe you know it, but it's important that we understand it a little bit also. So we have the zeolite phases. The zeolite phases, and this contains zeolites. Essentially, they are formed from zeolites. The most common type is Weireckite. You read up the formula. Lamontite. There are several others. It's no use writing the whole name. And then you have analcime. These are some of the characteristic minerals of the zeolite phases. The occurs, you can see this is 4 kilobars roughly. This is 200 degrees centigrade. So you have sedimentary rocks tipping here. It's in the very low pressure temperature regime. You have the zeolite phases. And then you go up and you get PP, which is brainite, pampelite phases. These are the two characteristic minerals. These are the two characteristic minerals. prehnite and pampelite, and you better read up the founders, prehnite and pampelite. Now, prehnite and pampelite does not stabilize in the pellitic rocks. They are never stable in the pellitic rocks. They are mostly a characteristic of mafic rocks. Some of them are characteristic of dirty, marly, sedimentary rocks, carbonate rocks. Then we have the blue schist phases. And now we have the very famous mineral glaucophane, which gives it the blue color, lawsonite or epidote. So we have glaucophane, lawsonite and epidote, and we have also plus minus chloride. This is the blue schist phases. The color of glaucophane is blue, so you get blue schist phases rocks. And then you have the eclogite phases. And many of you will be very excited because this is where you find garnet and another mineral by the name omphacite. And another mineral by omphacite. And this omphacite is nothing but sodium aluminium planoperoxide. So this is a garnet omphacite rock which forms the eclogite phases. So you have the zeolite phases with the zeolites, lamontite, etc. Prehnite, pampelite phases. Now you can see, if you go from zeolite phases to prehnite, pampelite phases, then you have to stabilize prehnite, pampelite and forget about zeolites. So obviously this is a reaction boundary by which prehnite and pampelite stabilizes in metamorphic rocks as you go up pressure from the zeolite phases. Right? Up pressure from the zeolite phases, and you can see prehnite, pampelite is here, and you have the blue schist phases where you have glaucophane, lawsonite, epidote plus minus chloride. So obviously this reaction boundary takes out prehnite, pampelite, and you get glaucophane, lawsonite phases. So this is what all these black lines are essentially reaction boundaries. We won't be studying all of them, we don't have the time, but these are essential things. These are reaction boundaries. Then we come to, I will erase this. This, you can imagine, this is high pressure. This is high pressure. High P by T. Barial metamorphism. Typical barial metamorphism. Now we go into the one that we will be studying more about because these are the most common ones. I'm not saying that the blue schist phases is not common. If you have subduction zones, you will have blue schist phases. That's not the issue. So now we have the green schist phases. Now we have the green schist phases. The classic mineral here is chlorite. And then you have plagioclase, but the composition is albite. That's very important. Chlorite, plagioclase, this is a characteristic assemblage, but the composition is albite. And then you have actinolite. And you have plus minus suicide. Yeah, I will just clarify one thing before we start. I have two formulas, Ca2L3Si3O12OH. Now this is cladiozoicite. But if you replace aluminium by ferric iron, Ca2Fe3Si3O12OH. Now that's epidote. So essentially, cladiozoicite epidote is ratio of aluminium by aluminium plus ferric iron. Epidote does not contain a lot of divalent iron. It contains trivalent iron. So now you have chlorite, plagioclase, albite in composition, actinolite zoisite. Chlorite and actinolite together, both of them have green color and they impart a greenish color to the rock. And since they are flaky and acicular, they give you a schistose appearance. So that is why these are called green schist faces. Now, if we go to the epidote amphibolite facies, epidote amphibolite facies. Now, let me tell you one thing. I will clarify a lot more. Actinolite is also an amphibole. Actinolite is also an amphibole. It's a low aluminium amphibole. Okay? Actinolite is also an amphibole. So when I say epidote amphibolite facies, I mean some other type of amphiboles. So now we have plagioclase, but the composition is now albite oligoclase. Plagioclase, but the composition is now albite oligoclase. So you can see from green schist faces where the plagioclase is albitic to the plagioclase and the epidote amphibolite faces, you get albite plagioclase. So you get a calcification of plagioclase. Calcification of plagioclase. We will see how this is done. And then you have hornblende, and sometimes you have two hornblendes. Sometimes you have two hornblendes, plagioclase and hornblende. Sometimes you have two hornblendes. And then, as the name implies, you have epidote plus minus garnet. Plus minus garnet. This garnet occurs at the high pressure side. You know garnet is very dense. So when I say plus minus garnet, so you can imagine at higher pressure you would have garnet and you would have plagioclase, hornblende, epidote plus minus garnet. So obviously this boundary, green schist faces boundary, here you can see the green schist epidote amphibolite faces boundary is by which chlorite is exhausted. So essentially this reaction here is a chlorite out reaction. Chlorite out reaction. It is not a amphibole out reaction because here you have actinolite and here you have hornblende. I will tell you a lot more about hornblende. And it is also not epidote zoisite, and plus minus garnet can occur at higher pressure in all assemblages. So essentially it is chlorite goes out across the epidote amphibolite faces boundary. So this boundary essentially marks chlorite is gone. So there's a chlorite out reaction. Then we have amphibolite facies. We have amphibolite facies. And here the classic assemblages, again plagioclase, but this time oligoclase andesine in composition. Plagioclase, oligoclase andesine. Once again you see plagioclase gets calcified. And then you have hornblende. Mark, it's not two hornblende, it's one hornblende. And there is no epidote here. There is no epidote here. Plus minus garnet. Plagioclase, hornblende, plus minus garnet. Now, therefore, the boundary between the epidote amphibolite faces and amphibolite faces, which is this line here, this is essentially epidote out reaction. It's epidote out. That means if you're going on a progressive metamorphism, this was chlorite out, this is epidote out reaction. It is nothing in, it is out. As we go into a progressive metamorphism, this is chlorite out, this reaction. This reaction is epidote out. And then we have granulite facies. And then we have the granulite facies. And this you have again plagioclase, and it has andesine in composition, mostly andesine in composition. It has there is another mineral that comes into the amphibolite phases. I've not written it. It's plus minus clinopyroxene. That's another mineral that comes in the amphibolite phases. Plagioclase, hornblende, plus minus garnet, plus minus clinopyroxene. And the granulite phases, you have plagioclase, then orthopyroxene is the key mineral. And then you have clinopyroxene. This is plus minus. Then you have plus minus hornblende. And then you have plus minus garnet. So that's the assemblage of the granulite fishes. Plagioclase, andesine in composition. Orthopyroxene is a very key mineral which does not appear here. Clinopyroxene could contain. Hornblende could contain. Plus minus garnet. So now, this boundary now, you're talking of amphibolite fishes to granulite fishes. This boundary, this one is an orthopyroxene in reaction. This is chloride out, this is epidote out. This one here is orthopyroxene in. Orthopyroxene in reaction. That is very, very important. Here also we will talk about later more great details on granulite eclogite phase boundary. We will study these boundaries one after the other, right? But first what we will study here is, so you can understand, the reaction boundaries and essentially phases boundaries are essentially designated for something here, chloride. If you go up pressure, chloride out, epidote out, orthopyroxene in. Orthopyroxene in. And that's very important. So all these we will first study, in our first class we will study this boundary. I will first study this boundary. Amphibolite to granulite. And then we will go from granulite to eclogite. This is how we will go. First we will look at amphibolite, granulite, what happens here, and then granulite to eclogite, what happens here. And then later we will study this one. Green schist phases to epidote amphibolite phases to amphibolite phases. But to begin with, we will start amphibolite to granulite to eclogite, and then we will study green schist to epidote amphibolite to amphibolite. Have you understood? But before doing that, I think it is very important for us to study certain minerals very carefully. The most complicated mineral in this are three minerals essentially. See, all the minerals that I have written are solid solutions. But one mineral that needs to be studied in great detail, and we will do that, is amphiboles. Amphiboles. People have a lot of difficulty in trying to understand amphiboles. So first, we will take up the case of amphiboles. Right? Now, before going into that, let me tell you, take you back to the green lines. You can see, I think I have made a mistake. Anyway, melting is more common in the granulite and upper temperatures of the amphibolite phases. Upper temperatures of the amphibolite phases and the granulite phases. I think I will erase this, and please remember the mineral assemblages. Say for example, granulite phases, plagioclase, orthopyroxene, clinopyroxene, hornblende plus minus garnet. If someone asks you, what is the granulite phases assemblage in a pellitic rock? And this can be very varied, but many of these assemblages will not appear. Orthopyroxene, yes, it can appear. You can have cordierite, you can have garnet, you can have sapphire, you can have a whole set of minerals. Orthopyroxene, whole set of minerals. But you will not have this particular assemblage with hornblende in it. You will not get it. That is because of the diversity of the chemical composition. Right. So now, first we will talk a little bit about Let's see what time I have. Wait. Let it dry a bit. It's too wet. Let's talk a little bit about amphiboles. And this is very important for us to understand amphiboles. These are really very complex words, very complex. The easiest amphibole to identify is to write a formula. I think if you remember this formula, everything else becomes easier. This is Mg7Si8 O22 OH whole twice. This is the simplest of amphiboles. The name of this amphibole is anthophyllite. And it forms a solid solution with another mineral, which is Fe7Si8 O22 OH whole twice. And the name of this mineral is grunerite. So this is called, because iron and magnesium can replace each other because of their very similar identical charge and very similar ionic radius. So Mg7Si7, Mg and Fe form a continuous solid solution series. Anthophyllite grunerite also forms a solid solution series. By the way, both anthophyllite and grunerite are orthorhombic. They crystallized in the orthorhombic system, and they are also called orthoamphiboles. Orthoamphiboles. They crystallize in the orthorhombic system. It's very similar to orthopyroxene. Then you have another mineral here, which is called Mg5Al2, Al2Si6, sorry, O22, OH O2. And the iron end member, Fe5, Al2, Al2Si6, O22, OH O+. Now you see here, what is the replacement here? The replacement is, you see here, Mg7, it's Mg5. So and here you see, this side, it's 2 plus 6, 8, and this is 5 plus 2, 7. Here also, 6 plus 2, 8, here it's silicon. So Fe7, Mg5 and Al2. So what happens here, this is the tetrahedral site, and this is the octahedral site. This is the tetrahedral site, and this is the octahedral site. This is the octahedral site, and this is the tetrahedral site. So there are 8 tetrahedral sites and 7 octahedral sites. And here you have identical. What is how will I remember if I have anthophyllite? You can see here the replacement is Mg2 plus, here you see Mg2 plus Si4 plus. You see that? And that you replace by Al3 plus octahedral plus Al3 plus tetrahedral. Octahedral plus tetrahedral. So I take out one magnesium plus one silicon and replace it by two aluminium. Here in the total thing, actually it is 2Mg2 plus to 2Si4 plus this and this. It's a double formula. So what happens, this element, this was anthophyllite chloride, and this is called gidrite. Gidrite. This is the gidrite solid solution series, and this is the grunerite, anthophyllite grunerite solid solution series. Both of this are orthoamphipoles. Both of this are orthoamphipoles. This is replacement of a magnesium by silicon, magnesium plus silicon by aluminium, and twice of that. So these are both orthoamphipoles. But there is a possibility you have 7 octahedral ions, but you can replace 2 of the manganese by calcium. And so you have Ca2, Mg5, Si8, O22, OH whole twice. Now you know the name of this mineral. This is tremolite. This is tremolite. And you have the iron end member, which is Ca2, Fe5, Si8, O22, OH whole twice. This has a nice name. It's called Cummingtonite. This is called the Cummingtonite solid solution. Nice name, no? Cummingtonite. Solid solution of tremolite and actinolite. They form the Cummingtonite solid solution series. What is the replacement? 2Mg/Fe by 2Ca. Both of them have 2 charges. So that is the replacement. 2 of the octahedral ions. So this is now octahedral. This is octahedral. This is tetrahedral, and this one is cubic. So this is what has happened. Since you notice that calcium has a larger ionic charge, ionic radius than magnesium or iron. So calcium have to shift in a place so that it is surrounded by 8 oxygen atoms, because it's too big for 6 oxygen, for 6 nearest neighbor ions. So what happens here? This one's replacement is 2 magnesium from here is replaced by 2 calcium, and this is 8-fold coordination, 6-fold coordination, 4-fold coordination, and similarly here. And the system is coming to light. Tremolite, actinolite series. Then what comes out is a simple substitution. So this is coming tonight. And you remember tremolite, actinolite. And then what happens? Another type of replacement occurs. And here, one silicon here is replaced, Si4 plus is replaced by Na plus Al3 plus. This is the substitution. So what happens if you take out a silicon? So you will have aluminium, 1 aluminium, and then silicon is 7, O22, OH whole twice, and here magnesium 5 remains the same, calcium 2 remains the same, and this is what is sodium comes in. So this is where sodium comes in. This position, which has a 9-fold symmetry element, 10-fold symmetry element, this is vacant here. In tremolite, there is no sodium or potassium. So this position is vacant in tremolite, but it is there covered with sodium or even potassium. Some of transition of calcium also occurs. So this is, and the mineral here is called edenite. Mineral here is called edenite. And the iodine member, which is, I will also write a blank. So it's a blank here. And so it is NaCO2, Fe5, Al, Si7, O22, OH4 twice. And this is the edenite series. Right? Then what we do is we make another substitution. And this time we take a silicon and take a magnesium, like here. Take a silicon, take a magnesium, replace it by aluminium. So silicon 4 plus Mg2 plus, and this should give you Al3 plus Al3 plus. Remember, 2 of the Al goes into the aluminium and the octahedral side. So now we have NaCO2, but now 1 magnesium is lost because you have taken it here, and 1 aluminium is added. So you have Mg4 Al, and now here 1 silicon is taken away and another aluminium is added. So you have Al2 Si6 O22 OH4 twice. So once again, from Mg5 plus Si plus Mg, so Mg goes down to 4, Al silicon goes down to 4, and this position is now replaced by 1 aluminium, and this position is replaced, adds 1 more aluminium to the pre-existing aluminium. And so you have NaCO2, Mg4, Al, Al2, Si6, O22, OH4 twice. And this series is called the Pargasite series. This is called magnetio-Pargasite. This is called ferro-Pargasite. And the whole thing is called the Pargasite series. Here, magnetio-Edenite, ferro-Edenite, the whole thing is Edenite. This is tremolite, actinolite, the whole series is coming. One more substitution occurs. Now this is slightly different. You take Na plus Mg, mark my words here, and replace it by Al3 plus. Right? So you have Na is taken off, so you get it back to your blank. Ca2, nothing happens with it. You have taken away 1 magnesium, so you have Mg3, but you have added an aluminium in the octahedral position, so you have Al2, and then you have Al2, and you have Si6, you have O22 and OH4 twice. Similarly here, blank, Ca2, Mg3, Al2, Al2, Si6, O22, OH4 twice. And this is called Shepakite. This is called Shepakite. So now, we have all these are clinoamphiboles. These are all clinoamphiboles. All of them are in the monoclinic system, so they have inclined extinction. Say all of them are clinoamphiboles, all of the whole. Cummingtonite, edenite, Pargasite, Shepakite, all of them are clinoamphiboles. And these are the substitution schemes which you have to remember. So once you get this, you know how to derive the different chemical formula. You don't have to mug it up. So when you talk of hornblende, you essentially talk of a solid solution of the whole thing. That is what you see of hornblende. So you can see how complex now your hornblende, your amphibole has become. First of all, there are 2 amphiboles, orthorhombic amphiboles and monoclinic amphiboles. Orthorhombic amphiboles are anthophyllite, grunerite, and kettlerite. Clinoamphibols are coming tonight, edenite, pergasite, schermakite, and a solid solution of this gives you hornblende. Right? So hornblende is not a distinctive component. The distinctive components are all these. Now, I have not taken in titanium or ferric iron or potassium. I have not taken. If I take this, then the number of components in the amphibole becomes so large, we will forget reading about it. So there are, for example, chiasotite, berkerikite, richterite. There are many different types of amphiboles. If you take in potassium, if you take in ferric iron, if you take in titanium, we have restricted ourselves to a very simple system, NaCaFeNgAl SiO2H2 system. That's all we have referred to. And OH can be replaced by fluorine, chlorine at the minimum. So hydroxyl ion that you have here can be replaced by fluorine and chlorine. So you can have chlorohornblende and fluorohornblendes. So essentially hornblende is a hugely complex mineral that we should know how to deal with it. We will talk about hornblendes much more. So right now I think I wind up. We will continue with this in the next class.